if you're at this point in the DC circuits, you should take your hat off actually and congratulate yourself that you've got a long way through this subject. I've put this video together just to round off some of your skills and make sure that you're happy and you know that you really are set for a reasonable result, hopefully an excellent result in the you know, in the unit knowledge test, which you're obviously preparing for. A few things I just want to say about it. Look, it is an assessment. When you're reading the questions, please read the questions. They're not trying to trick you, but they are trying to ensure that you do have the knowledge in the assessment. So, you know, there will be individual words which, if you misconstrue, might lead you down into an incorrect answer. So look, do really read the questions, realise that you are doing an assessment, and look, this is a pretty tough assessment. It is, as I've said to you, it is the same assessment that the electrical apprentices would do, and you could certainly argue that it's the most difficult subject for a first year electrician. So you know, it's up there, and like I say, you should be pretty happy that you've actually got yourself here, because there's a fair bit of work to even get to be considered to have a look at the unit skills test, or the unit knowledge test, sorry. So anyway, a little bit about it. It is about 72 questions long. It will take you approximately 3 hours to do it. Please realise that you know, I will set a time for you to start. If I say to you on, you know, this afternoon at 3 o'clock you'll start, the test will the clock will start ticking at 3 o'clock. So if you don't log on and at 3 o'clock, well, you're chewing into your time. So if you find yourself not, you know, running out of time, that's fine. It may well be a 3 hour duration, but as far as the vocational educational and training rules of assessment are concerned, you can certainly have more time to do it. So please feel free to, you know, if you can't get it done within the 3 hours, don't race the questions. It's better to leave them completely blank. So you might get 50 questions done in 3 hours. Better to do that. At least then you can have a discussion with your, you know, with the assessor, and in this case would be myself, and I would see that you haven't attempted questions 51, 52 onwards, and I'd just simply re-release the test for you. You have another 3 hours, and that would be classed as your first, you know, part of your first attempt. So whilst most people do manage to get through it quite easily within 3 hours, it's an arbitrary time, you know, to do the thing. The unit knowledge test is only going to ask you questions that you have already answered in the topics. So there are, I think there was 15 topics in the DC circuits. You will get those type of questions, and indeed shortly we'll do some we'll have a look at some typical questions, so you actually sort of just to refresh and so forth. All right, in relation to being deemed competent within the unit knowledge assessment, you must get at least 55% correct answers, 55% of the answers. Otherwise we won't, if you like, you'll have to redo the assessment again. So if you do get 75% or above, we mark that down as your first attempt, and indeed if you get 100% on your first go, you're done and dusted, you're finished. But if you get 75% on your first go, you will not have to answer those questions again, as long as you get the other 25% in the next two attempts. So so you might get 80 in the first attempt, and then on your second attempt you might get 10% more right. Those questions will be, you'll have to redo the questions that you didn't get correct on your first attempt, and then on your third attempt you will be again given an opportunity to do similar questions on the same topics that you didn't or you haven't answered correctly, and if you get another 10%, then that would be 100% over 3 attempts. That would be would then allow you to be deemed competent, and your assessment would be complete. If you do not receive 100% over the 3 attempts, then you would have to go back and redo the full unit knowledge test again. So just to reiterate here, from Energy Space, you have completed topics 1 through 15, and you have received at least 90% in all the topic quizzes. And so really, if you've been working through those topic quizzes and receiving 100% or 94% or those sort of marks, this unit knowledge test is going to retest you on all of those topics that you can see here. Series circuits, parallel circuits, capacitance, and so forth. So you'll notice that on the following sheets, the typical question, it will also have up there where the question comes from, so from what topic. So if you don't understand one of the questions that we'll be looking at shortly, at the top of the page it will have the topic number, and of course you can go back into Energy Space and have a look at that topic and review that topic to make sure that you are across it, this is what preparing you for the unit knowledge test is all about. Okay, so look, having a look at a typical question, and this might be question number 1 of your unit knowledge test. It is from topic 1, as you can see from the top description there. So if you don't understand this question, this is I'm trying to show you the format that we're going to be following here. So this question is from topic 1. So if you wanted to find out a more detailed answer than I'm going to give you here, you would look back into into Energy Space, into topic 1. All right. So the first question might be worded as such: to allow electricity to be transmitted over large distances, the voltage is first, and then we have four answers, four to choose from. Now you could choose converted to DC by a transformer. You could choose storing in a battery bank. You could choose stepping down by a transformer or stepping up by a transformer. Now you should be sort of going, yeah, okay, got this. Look, the answer is clearly stepping up by a transformer, because if we're going to transmit electricity over a long distance, we want the voltage to be very high, and therefore if the voltage is high, the current is low, and if the current is low, that is a more efficient way to transport electricity, because we do not need to have large heavy conductors. So if we transform the voltage up to a high voltage, we have a lower current, so we have smaller conductors. So that would be so your answer, you would suggest would be stepping up by a transformer. So a photovoltaic array, which is a solar panel, supplies a constant current of 3.2 amps for a period of 5 hours and 4 minutes. Calculate the total quantity of electricity produced. They're asking this question in quantity of electrical charge, which is coulombs, or Q. So the formula that we need to use is Q is equal to I on T, and I guess just to refresh your memory here, Q is equal to 3.2 amps multiplied by the time that 3.2 amps was available, which was 5 hours and 4 minutes. But the time in the equation is measured in seconds, so we have to convert 5 hours and 4 minutes into seconds. So to do that, it's 5 times 60 to give it to you in how many minutes, and then there's 60 seconds in a minute, so you times that by 60. Anyway, you do all the maths, and you end up with a quantity of charge being 58,368 coulombs of charge. Please note that the question then moves on to say that please provide your answer to 3 significant figures, which means that you round up or round down, so therefore your answer in yellow is 58,400 coulombs of charge. If you're having trouble with this, like all of the following questions, you need to go to topic 1 and have a look at that. The LMS, the energy space clearly explains how the maths is done, and there are some worked examples back in topic 1. A 100 volt battery bank is used to supply a 900 ohm load. It could be a resistor, light bulb, whatever it might be. The circuit current will rise significantly to a dangerous level when, option A short circuit develops across the circuit conductors. B, an open circuit develops in the system. C, the battery bank is disconnected. A, B, C, D, the load is disconnected. Look, I've drawn there a little bit of a diagram there just to get, which is what I think of in my mind. 120 volts across a 900 ohm load. There will be a certain amount of current that will flow in that via Ohm's law. V is equal to IR. Once we transpose that to I is equal to V on R, 12 divided by 900 is equal to something, some amount of current. Not a lot. All good. If a short circuit develops across the conductor, which I've drawn in red, then Ohm's law then dictates that I is still equal to V on R. That's 120 volts divided by 0 ohms, or because a conductor has a very low resistance. That would be infinite lots. A huge amount of current will flow out of that battery bank, so that's the dangerous condition. So obviously the A is the correct answer. A short circuit developing across the circuit conductors. Once again, if you're having problems with that, understanding any of that, topic 1 is where you should go. Whilst I don't particularly agree with the way the energy space continually asks you to change things to 3 significant figures and arguably sets up little well, they're not traps, but they're little things that sort of are meant to be confusing to you. This problem is relatively easy once you can read the question correctly. So let's have a look. The resistance of the load in the circuit pictured above has a 425 ohm resistor. Calculate the current flowing through the circuit when the switch is closed. So provide your answer in the units indicated, which is milliamps, and also round it up to 3 significant figures. Simply Ohm's law, voltage divided by the resistance, so 50 volts divided by 425 ohms is 0.1176 amps. 117.6 milliamps is the correct answer. However, they have asked you to express this to 3 significant figures, so you round up because the 0.6 is above 0.5, so the answer is 118 milliamps. Once again, it's straight out of topic 2. If you're having troubles with any of that, please refer back to topic 2. Which of the following resistors could be connected to a 50 volt DC supply without sustaining damage? So what we're saying there is that if we had a 50 volt supply and we connected a 2k 1 watt resistor across that supply, obviously there would be some current that would be drawn from the supply, and depending on what the wattage value of the resistor is determines whether it would be able to sustain that voltage and current running through the resistor. That is simply worked out via the formula V is equal to the square root of power multiplied by the resistance. You can see in the yellow that the maximum voltage that the first option, the 2000 ohm or the 2K 1 watt resistor, it could only be connected across a 44 volt supply. Any higher than that and that resistor would fail. Likewise, the 500 ohm 3 watt resistor could only handle 38.7 volts before it failed. And the last option, option 3, the 1.4K or the 1400 ohm 3 watt resistor, could handle 64.8 volts as its Vmax. So as the supply voltage is 50 volts, we need an answer to be over 50 volts. So the only one that's over 50 volts is the third one, the one in blue, which is would be quite happy sitting on a 50 volt supply, as it can handle 64.8 volts. Once again, a very standard question, and that one will come up in every unit knowledge test in one form or another. If you have trouble with that, have a look back at topic 4. Once again, a question that is surely going to be asked in the unit knowledge test. Which of the following diagrams shows the correct method of a wattmeter to measure power in a DC circuit? Firstly, you'll see on my little diagram down the bottom right hand side, recapping of course that a current meter, an ammeter, is connected in series with the load, hence the red line. Current flows through the ammeter, and in blue the voltmeter is connected in parallel across the load to measure the pressure drop or the voltage drop or the voltage potential difference across the load. So that's drawn in blue. If you just take a moment to have a read of the question, it talks about a wattmeter. Watts are measured as a measurement of power, and power is equal to volts times amps, as illustrated by the yellow formula. If you look at the top drawing there, well, there were 1, 2, 3, 4, 5. So there were 6 options there on how a wattmeter could be connected across a load, to measure the power consumed in a load. You have those options. Which one is correct? What you need to realise is that the voltmeter, the top one, is the correct answer, because the as you can see, I've drawn the voltage legs on it in blue, and the current flows through the meter. Once again, a classic question out of topic 4. Which effect produces an EMF, an electromotive force, when a temperature differential is created at a junction of 2 dissimilar metals? Of course, I'm thinking of the topic 6 diagram, which says that if you have a thermocouple, which is 2 dissimilar metals twisted together at a junction, and you heat it with a Bunsen burner, that is what this question is describing. So which one is it? It's certainly not an electrochemical. That would be a battery. It's not a photoelectric. That would be a solar panel. Not piezoelectric. That would be a crystal which is placed under pressure. A thermoelectric. Thermo being heat, electric effect. The answer is the bottom question. Straight out of topic 6. Increasing the load current in a given circuit from 1 amp to 3 amps will cause the power loss in the circuit conductor to double, go up 9 times, increase by a factor of 3, or triple. Well, tripling and going up by a factor of 3 is the same thing. So anyway, but that's interesting. Let's work it out. So what the question is saying is, if the resistance of the cable is a given, and I've assumed it's 1 ohm. So the resistance of the cable is 1 ohm in both the yellow and the turquoisey blue. You can see that the power is equal to I squared R. So 1 squared is 1 times 1. 1 times 1 is 1, so that's 1 watt of power consumed in the first circuit. And if we increase the current by up to 3 amps, 3 squared is 9. 9 times 1 is 9, so 9 watts. So it increases by a factor of 9 times. Once again, straight out of topic 6. Two very similar questions here, but worth going through them both. The first question on the left-hand side, the A, the one on the top left-hand side, the variable potentiometer. That is a variable carbon filmed resistor, very commonly used as a volume control in your stereo. The one underneath it, B, is a wire wound resistor. It also has a center pin as well, which can be moved, so it is a variable wire wound resistor. Whilst the two units on the right hand side, the A is a LDR, a light dependent resistor, and we've used those many times on in our practice and so forth. B is a NTS, which is a negative temperature coefficient resistor, and thermistor is a thermistor. There you go, that's the actual correct answer, a thermistor, which is a resistor that changes its temperature in a negative format. So as you heat it up, the resistance goes down because it is an NTS, but it is a thermistor. Straight out of topic 7, types of resistors. When a resistor in a set of series connected resistors becomes open circuit, the current in all of the other resistors will, well, how many times do we say that the current in a series circuit is constant? So the current flowing through in the diagram in red there is showing that the current flowing through all of those resistors is the same, and that's the definition of a series circuit. So if you have where any of those resistors goes open circuit, the current will not be able to continue around the circuit, so the current will drop to 0. Straight out of topic 8. Which of the following items of equipment are typically connected in series in an electrical installation? You can see by my figure A, that is a series circuit because the current is constant in a series circuit, whilst the circuit I've drawn, B, is a parallel circuit because there are branch currents, and light number 1 and light number 2 are in parallel. So the question says, which of the following items of equipment are typically connected in series in an electrical installation? A motor and a circuit breaker. Well, that would be the same as a fuse and a motor, so that is the correct answer. Okay, this one is looking a little bit scribbly, but look, the question is as per the diagram on the left hand side, which is 3 resistors in series, all connected to a 120 volt DC supply. The R1 resistance value is given at 25 ohms. There is no resistance value of R2. There is, however, a resistor R3 of 19 ohms with 32 volts across that resistor. That's the giveaway there, I guess. Look, let's have a look at the question. For the circuit pictured above, calculate the following, providing your answers in the units indicated to 3 significant figures. The first answer, the supply current. Okay, so the supply current is the total current. Second, B is the resistance of R2. So we need to calculate that one, and the total circuit power. Okay, so let's start to have a look. What we don't know, and hopefully you should be able to see, is that we need to calculate the current in the circuit, because if we calculate the current, we'll be able to use that current through each of the resistors. So number one is IT, that's the total current, is the voltage across R3 divided by the resistance of R3. So that's 32 ohms divided by 19 ohms gives us a total current, or the current through R3 at least, of 1.684 amps. The current through R3 is the answer in yellow, and of course that is the total current because the current in a series circuit is constant. That is your first answer, the yellow one. Okay, moving on to B, the resistance of R2. Okay, we need to find a couple of things for R2, and one of them is the voltage across R2, which is 46 volts. And we've calculated that by by calculating the voltage across R1. Because we know that the R1 is a 25 ohm resistor, we can multiply the 25 ohm resistance by the current in the circuit, which is 1.84. We end up with 42 volts. So there's 42 volts, that is the blue, light blue, across R1. If we know, therefore, if we know the voltage across R1 and we know the voltage across R2, we can simply use the formula VT is equal to VR1 plus VR2 plus VR3, and through that maths there we can simply deduce that the voltage across R2 is 46 volts. Therefore, if we have 46 volts across R2 and we have a current of 1.68 amps flowing through R2, we can work out R2, the resistance value of R2 in the green, which is simply Ohm's law. So R2 is equal to V2 on I2. 46 volts divided by 1.684 gives us a value of 27.3 ohms. So we now know the value of R2. That is the green answer. That is the second question. Okay, the last question is calculating the total power. Possibly the easiest thing to calculate. Power, PT, is equal to volts times amps. The total voltage is 120 volts multiplied by 1.684 watts. 1.684 amps gives us an answer of 202.08 watts. Rounding to three significant figures, the answer for the total power consumed by the circuit is 202 watts, given in the the reddy brown colour. Alright, once again, that's a fairly standard question for the unit knowledge test. If you have troubles with that, please refer back to topic 8. I would suggest this type of question gets asked 3 or 4 times throughout the unit knowledge test, but which of the following equipment is typically connected in parallel in an electrical installation? Your 4 answers are a control switch and a light fitting. Well, look, the simplest way to think about this is in a series circuit the current is constant. Now, so we're asking for what is typically connected in a parallel circuit. So if the current is constant through the switch and the light fitting, in other words, if the same current flows through the switch as the light, that means that that circuit is a series circuit, and obviously not a parallel circuit, so is not the answer. So in a switch and a light fitting, you can see by the very rough drawing I've given there that the circuit current is constant. Whatever flows through the light flows through the switch, so that is not the answer. A motor and a circuit breaker, once again the circuit breaker is the switch and the motor is the load. Whatever flows through the switch flows through the load, so that once again is a series circuit. An RCD and socket outlet, that's a little bit more difficult, but you can see that it is still in series. That is the current flowing through the active switch goes to the active pin of the power point, flows out of the power point through the toaster or whatever's plugged in, flows into the neutral, and the neutral current flows back through the neutral side of the residual current device. That is a series circuit. The last one, socket outlet on the same circuit. Well, if there is a toaster plugged into the first socket outlet and an iron plugged into the second outlet, the current in the active conductor splits, so it is not the same. The current in the active conductor will be the addition of socket 1 and socket 2. Therefore, it does not have the same current flowing through, so therefore it is a parallel circuit. If you're having troubles with that, topic 9 is where you should go and review the information inside topic 9. A very standard question for the unit knowledge test, straight out of topic 9, and if you've completed worksheet 7 or 8, should have no problems with this. The question is, for the circuit pictured above, calculate the following, providing your answers in units indicated to 3 significant figures. The equivalent resistance of the circuit to be measured in ohms, the supply current measured in amps, the total power dissipated by resistor number 1 in watts. Okay, to calculate the resistance, it's simply using the parallel formula for resistances, which is the 1 on RT. Using your calculator, simply 15, 1 on X plus 5, 1 on X plus 10, 1 on X, 1 on X your answer. You'll end up with 2.72 ohms. That's an answer in yellow. Part 2, calculating the supply current. To calculate the supply current, we need to know the total resistance of 2.73 ohms, which has a 24 volts supply connected to it. So IT is equal to VT divided by RT, which is 24 divided by 2.73. It's 8.8 amps. Answer in blue. And the power dissipated by R1, we need to calculate the current through R1, which is shown in that lilac magenta colour, which is simply, the current through R1 is the voltage across R1 divided by the resistance of R1. Because it's a parallel circuit, we understand that the supply voltage is 24 volts across R1 and divided by 15 ohms, which gives us 1.6 amps through R1. So to calculate the power in that resistor, it is simply 24 volts across it multiplied by 1.6, which gives us 38.4 watts. Answer in green. Once again, if you're having trouble with this, relook at topic 9. Also, make sure that you are well across worksheet 7 and in particular worksheet 8, and you should have no problems with these types of questions. Well, my drawings seem to get scratchier and scratchier as the days goes on, but another question which reads, 3 15 watt lamps are connected in parallel to a 12 volt supply. If the second lamp goes open circuit, the supply current will, the formula for the supply current is in yellow, and it's equal to the summation of all the branch currents in a parallel circuit. So whatever the current is flowing in L1 to produce 15 watts is something, and the same again as in L3. There's some current flowing through L3 because it's consuming 15 watts. But L2 was a 15 watt lamp, but it's open circuited. The filament has blown up inside it, or there is a loose connection for some reason. But at the end of the day, there is no current flowing through L2. So in magenta, there is 0 amps flowing through L2. So the total current will be reduced by, well, in fact, in this count, 1/3 of what it was. So the correct answers must be that the current will simply decrease. Answer given in green. Once again, straight out of topic 9, and I wouldn't be surprised if there's a number of these type of questions within the unit knowledge test. Hopefully by now this type of question is becoming quite pleasurable to do, and hopefully you are starting to see that this really is simply a game of chess. But the circuit given in this question on the top left hand side is simply a series parallel circuit, and you are required to calculate the equivalent resistance. Whilst I'm a little bit short on room, this is really not a maths problem, this is more about drawing pictures. But anyway, as you can see, if we were to add the resistance value of R2 and R3 together, that would give us 160 ohms. That 160 ohms is in parallel with 120 ohms. If we use the formula 1 on RT, etc., to calculate that, so we have a 160 ohm resistor in parallel with a 120 ohm resistor. The answer for that is 68.57 ohms. That resistor, as shown in figure 1 now, is in series with the 80 ohm resistor, and you can see that R5 and R6 have a resistance value of 120 ohms each. We should know by now that we can sum those together using the 1 on X formula and put it into your calculator and so forth, but please realise that if the resistance value is the same, 120 ohms and 120 ohms, and those two resistors are in parallel, the answer will be half the 120 ohms, which is 60 ohms. So therefore, in figure 1, we have a 68.57 ohm resistor in series now with 80 ohm resistor in series with a 60 ohm resistor. Simply adding those three resistors in series together, we have an answer of 108.57 ohms, answer given in yellow. And so the answer is 108.75 ohms. The only answers that you're allowed to give, however, are 208 ohms. Sorry, I might have given you the wrong answer there. The total resistance, of course, in yellow is 208.75 ohms. The closest answer to that is 209 ohms. They've obviously rounded that up. So answer is 209 ohms. For that, once again, should be nearly laughing at these type of questions, and if not, you really do need to go back over worksheet 7, worksheet 8, and having a good look through topic 9. Well, funnily enough, I'd got halfway through drawing this circuit out and had made a mistake that I had connected the batteries in series, and I've still left an incorrect answer. But anyway, let's read the question. If two 1.2 volt NiCad cells are connected in parallel to a supply of a 2 ohm resistor, then the supply current will be what? One of the options. Alright, well, these batteries are connected in parallel, so as per the drawing I have there in the centre of the page, so 1.2 volts in parallel with 1.2 volts gives us a supply voltage of 1.2 volts. So the current total, IT, is equal to VT on RT, which is equal to 1.2 volts, that's the supply voltage, divided by the resistance of the circuit, which is 2 ohms, which is 0.6 amps. So the top answer is correct. You'll see that I've marked 1.2 amps. That's because I originally didn't read the question and I put these batteries in series, which made the voltage 2.4 volts. So anyway, just be very careful to read the questions, draw the circuits. Anyway, if you have, I wouldn't think you'd have a problem with doing the maths on that one. Probably more of a problem of reading the question. Anyway, straight out of topic 9. Righto, straight out of topic 10, parallel circuits. The drawing in the centre of the page, and the question is, in the circuit pictured above, if R5 goes open circuit, then what will happen? The circuit current and circuit resistance will both go to 0. If you're not careful, you might tick that as a correct answer. But obviously, if the resistor number 5 is open circuit, in other words, there is no way current can get through that, there will be no current in the circuit, so the circuit current will fall to zero. However, the circuit resistance will go to infinity, which is the second answer. The circuit resistance will be infinite and the circuit current will reduce to zero. Please read the questions. Some of these look daunting but are more of an English test than a DC circuits test. Anyway, straight out of topic 10. The only problem I have with this question is actually understand what it's asking. In the picture on the top left hand side, there are two lamps connected in parallel with each other and a switch and a fuse connected to a supply. The question is, complete the following statement in relation to the lighting circuit diagram pictured above. And it states, lamp 1 is connected in series with switch 1. That is correct, using the yellow diagram there. Number 2, lamp 2 is connected in parallel with lamp 1. So essentially, to work these sorts of things out, just remember that the current in a series circuit is constant. So the current that flows through the switch is the same that goes through the lamp, L1, and the different currents in lamp 1 and lamp 2. Straight out of topic 10. Okay, for the circuit pictured above, calculate the following, providing your answers in the units indicated and to three significant figures. On this one, guys, look, my answers might not be strictly correct, but they're certainly in the ballpark. It might be a couple of decimal places out, but essentially this is straight out of topic 10. If you've done worksheets 7 and 8, this should be really quite simple. Just bearing in mind that R1 and R2 are in series with each other, we simply add those together, and R4, R5 are also in series, we just add those together, and then of course R3, R6 and the combination of R4 and R5 are all in parallel. That gives you your 40 ohms. Your total resistance value comes out at 260 with a current of 0.077 or 77 milliamps. We need to calculate the power in one of the resistors, so simply knowing the current through R1 we can calculate the power, which is 0.889 of a watt or 889 milliwatts, etc. All should be fairly standard. Hope I haven't made a mistake in one of these. If you're, you should be doing this yourself and on your own scrap piece of paper and making sure you get very similar answers to mine. Anyway, any questions on that one, refer straight back to worksheet 8 or in topic 10. What happens if the temperature of a current carrying copper conductor decreases? Okay, so it's a bit of a mouthful that. So what happens if the temperature of a copper cable reduces? Well, we must understand that copper has a positive temperature coefficient. That is to say that as the temperature of copper increases, so does the resistance. So the hotter a copper cable gets, the higher the resistance it will have. So therefore, if it has a higher resistance as the temperature increases, by virtue of the fact of Ohm's law, V is equal to IR, the voltage drop across that conductor will also increase. So the answer to the question is the voltage drop across the conductor shall decrease. Because the question is written backwards a bit, what happens if the temperature of a current carrying copper conductor decreases? So if the if the temperature of a cable gets hotter, the voltage drop will get higher. If the voltage on the cable gets less, the voltage drop will also decrease. That's a bit of a mouthful. Anyway, straight out of topic 11. Okay, these types of questions are quite common and they're straight out of topic 11. This one reads, calculate the resistance of a 6mm squared copper conductor having a length of 46 meters if the resistivity of copper is 1.72 times 10 to the minus 8 milliohms. Provide your answer in units indicated in the significant figures. Straight out of topic 11, there's about 5 or 6 of these different types of questions. You really do just have to have the formulas next to you when conducting the unit knowledge test, and you just have a look at topic 11 to do the calculations. Once again, a very typical question straight out of topic 11. Really, I can't really say much about it other than, as per the previous slide, ensure you are across the formula and realise where the figures go into the formulas. The one saving grace is that the unit knowledge test writes the question very similar to the documentation in topic 11. So if you can do the questions in topic 11, you should easily be able to do the questions in the unit knowledge test. The question here relates to topic 12, which is all about metering and so forth, and internal resistances of a voltmeter in this case. The question reads, in relation to the circuit pictured above, calculate the voltmeter reading if the voltmeter had an internal resistance of 18 kiloohms. What one needs to realise here, of course, is that if a voltmeter has an internal resistance, as you place it in parallel with R2, that internal resistance will affect the current flow in the circuit and alter the readings. So look, the maths is on the left hand side, but essentially when we have the 18 k ohm resistor connected in parallel with with R2, the parallel resistor is decreased to 2117.6 ohms, and that alters the current to 36 milliamps. And then we calculate the voltage across the 2117.6 ohm resistor at 76.6 volts. If the part 2 of the question asks us to remove the voltmeter from the circuit, which I've redrawn on the right hand side, very scribbly, and I do apologise, but this is supposed to be a brief overview of these questions. So on the right hand side in blue, you can see that the 2400 ohm resistor has a slightly less amount of current flowing through that now at 33.3 milliamps instead of 36 milliamps, and the voltage across that resistor then at that stage, without the ohm meter or the voltmeter being connected, is 80 volts. So you can see that when a voltmeter is connected to a circuit, it does have an influence, particularly if it has a fairly low, what we call internal impedance, and in this case the internal impedance of this voltmeter is 18,000 ohms, which is considered quite low. So anyway, topic 12. Not going to give you the answer to these questions here, but just realise that this would be a typical question. The best method or meter to be used to measure the resistance of 0.02 of an ohm would be a something or other tester, or a particular shunt. It's in topic 13. Realising, of course, that 0.02 of an ohm is a very small resistance value. An insulation tester measures megohms, and an ohm meter measures ohms, starting really from 0 ohms upwards. So 0.02 is a very low amount of ohms. So I would suggest either a long shunt or a short shunt. Please have a look at topic 13 to get a little bit more knowledge on which one that would be. Once again, not particularly wanting to give you the answer to this, but the question reads, which of the following checks would be the most effective method to confirm that the conductor core of a multi-core cable are continuous? I guess we could say there we might have a let's say a telephone cable which might be 50 meters long. What meter would you use just to confirm that the white wire in the telephone cable is connected to the white wire at one end and the white wire at the other end? I would have thought we would use that as a continuity tester. I would have thought we would use an ohm meter, just measuring on ohms. That probably would give us the right answer, I would think. But once again, in topic 13. I'm sure this is covered in topic 13, but I know that I've mentioned it a number of times, and that is that an IR tester, which is an insulation tester, which is a tester which is meant to test the insulation resistance of a particular cable. So that is trying to punch a small amount of current through the plastic insulation of a cable to another cable. So from, let's say, an active conductor to the earth conductor. In AS3000, as I've mentioned, we must use twice the applied voltage to test. So in this case, if the appliance is going to be used at 230 volts, the insulation tester must be set to at least twice the applied voltage, and so that would have to give you an answer, I would suggest, of 250 volts. But in topic 13, just letting you have a look at some typical questions. These are not difficult questions, but please do read the questions. Which of the following must be done prior to carrying out an insulation resistance test on the wiring of a 230 volt AC supplied circuit? So assuming the circuit is connected and live, you could argue the question is a little bit badly worded, but it does say that the circuit is energized at, well, it doesn't say it's energized, but it says it has 230 volts applied to it. If you're going to test that in any form, one would suggest you might like to isolate the circuit wiring first. Apparently covered in topic 13. Whilst I could give you the answer for these questions, really you need to go straight back to topic 13 if you cannot remember what that topic was about. I've just inserted a very small extract there in relation to short shunt and long shunt, but please, if you can't answer this question, and in fact, look, to give you an answer, the correct answer for that workings out is 492. So if you don't get that answer, then maybe you should go back and have a look at topic 13. Okay, just remembering that there are 5 time constants to fully charge a capacitor. So in this circuit here, it reads, for the RC circuit pictured above, calculate the time taken for the capacitor to become fully charged after the switch is changed to position 1. So once the switch is placed into position 1, the current will flow through R1, a 5K resistor, and slowly charge up that capacitor. The time constants can be calculated by TC is equal to RC, so that's the resistance times the capacitance. That's equal to 1 time constant. So remember, it takes 5 time constants to fully charge that capacitor. Also note that you might have following questions about bleed resistors and so forth. Please note that on that circuit there, that when the switch is in position 2, the capacitor is essentially drained in the reverse direction by using the 5K resistor as well. That is to leave the capacitor empty of charge, and in industrial situations these capacitors can get quite large, and leaving large capacitors charged up can be quite dangerous. So anyway, all in topic 14.